All right, in this video we'll illustrate some rapid drawdown examples, and I'm going to walk through, I think, 4 different scenarios. So this video may take a little while, but I think they're all important. So what I'm going to do is start out just by showing how the permeability of the soil actually influences whether or not you'll get a rapid drawdown failure. So what I'm going to do is add a scenario here, and I'm going to call it, we'll just call it Transient Seepage Analysis. Save and close. Okay, so then I'll go to this Transient Seepage Analysis, and what I'm going to do is specify, well, first I've drawn in this typical 4 meter high 2-to-1 slope levee that we've been using the whole time. And then these different examples will use different methods here. So I'm going to go to groundwater and then pick steady state finite element analysis, then advanced transient groundwater. And in this case, I only need 2 stages. I'm going to call this one initial and this one final. And the reason I need only 2 stages is that I'm only interested in 2 conditions. Steady state when the reservoir is up here, and then final when the reservoir is down there. And we're going to have a drawdown time of 3 days. So I'm going to put 0 for the initial and 3 days for the final, and we'll calculate factors of safety for both of those. And let's go to methods, and I'm going to click Spencer. By default, we should always use that one. I'll just do Spencer's method here. All right, so now we need to come over to our groundwater. I always start there. And I'm going to add a 0, 15,000 elements, and 3, the triangular elements are fine here, so I'll stick with those. And then, of course, we have transient groundwater also. So let's do steady state. Actually, I forgot to add one of those nodes here on the external boundary. So let me cancel the mesh. I'm not sure how to do that. I think this one, reset mesh. Okay. Now I should be able to add a vertex. If I go to geometry, here we go, and I'll add it at 26,7, which is where that water surface is. Okay, now we can come here, discretize and mesh. And I'm going to set the boundary conditions. So we're going to start out with a 7 meter total head boundary condition, and I'm going to apply it only to the steady state. So there's those boundary conditions, and then we're going to have a 4 meter high boundary condition that I'll apply to both steady state and transient. We'll put it there. Okay, so that's our steady state condition. Then transient, what I'm going to do is set a transient boundary condition, and we'll put a new function. So at 0 days, whoops, we'll call this drawdown. Okay, so at 0 days, we will have a total head of 7 meters, and at 3 days, we'll have a total head of 4 meters. So that 3 meters of water is going to be drawn down over the span of 3 days. And I'm only doing 2 points, which will assume a linear drawdown during that time. And then we will assign it here and there. Close. Okay, so that's our transient groundwater analysis. Now we need to go to slope stability and assign material properties. So I'm going to put in the same material properties we've been using, which I believe is 5 kPa and 30 degrees for the friction angle. And we will be doing an effective stress analysis here, right? So failures going this way and pore pressure changes will be entirely controlled by the seepage analysis. So one thing we're missing here that I talked about in the previous video is shear-induced pore pressure. Okay, there's not going to be any pore pressures caused by shearing in this case. They're all just going to be arising from the seepage analysis. So I'm going to go circular grid search, and then I'll just auto grid. Okay, and now let's set, one thing I didn't look at was the hydraulic conductivity. That's the whole point of doing this lesson. So if I go to hydraulic properties, I'll leave this at 10 to the minus 7. That would be a fairly like silty sand kind of material, not real free draining. Maybe I could make it even less, like 10 to the minus 9. This would be like a clayey sand, something that we definitely think will not be free draining during this 3 days, right? And we can do the compute, yes, and it'll run the groundwater simulation. And the transient seepage analysis does take a little while. When the soil's not very permeable, it's retaining a lot of water, and it takes the transient seepage analysis just a little bit of time to run it. And now we can run our slope stability analysis. I'll calculate here. Okay, and it's all done. And we come over to this page, and we got from Spencer's method, the factor of safety is 2.439 initially. And then that's the same as for the initial part of the transient seepage. And then the final is 0.348. And we're going to have this little failure way down here. Notice that the phreatic surface hasn't really moved. Okay, it's still way up here. It basically didn't change between 0 days and 3 days, just because the permeability is pretty low. So now what we can do is go back to our modeler and just change that hydraulic conductivity to be something that's more free draining. So I'm going to magically change this by 5 orders of magnitude, right? It's so easy to change that exponent. What we're really doing is making it go from like a clayey sand or a silt all the way down to just a free draining coarse sand. Okay, and then we'll rerun the seepage analysis. This one should run a little faster than the previous one. Yeah, that was faster indeed. And then we'll come to the slope stability and run the compute. All right, and we're ready to go look at the result. Same factor of safety here for the initial loading condition. Same here for this initial after 0 days. And then notice that now the phreatic surface is all the way down here at the bottom, and we have a factor of safety of 2.002, which that was before when we were doing the analysis. We were starting with the groundwater table here and then raising it up, and the factor of safety started at 2.002, and then when we raised it up, it went up. So indeed, this is doing what we think it should do, right? We're modeling the effect of drawdown just by adjusting the hydraulic conductivity of the soil. So actually, I think I'm going to stop the video here and divide this into 4 different videos so that you can conveniently watch just the one that you want.